Hello class, welcome to today's video on section 3.5, the trigonometric functions. As you're watching the video, please remember to take down important notes, vocabulary, formula, and equations. Feel free to pause, rewind, or even replay the video multiple times to get a clearer understanding. And don't forget at the end of watching the video to write down your summary in the notes and then submit the summary and your top question in the online whisk form before class. All right, let's begin. We've been dealing with the derivative, and we're going to take a look at finding the derivative of the trigonometric functions. And we're going to first start with sine. Even though we kind of already have an idea of what the derivative is going to look like, here we have the sine function. And if you remember, the derivative is the slope of the tangent line at each point. So if I were to try and look to see where the slope of the tangent line is highest, it seems to be highest at certain points, like right here, and right here. Well, right here. And it seems to be lowest at these points. In other words, the magnitude is the highest in the negative direction. And it seems to be 0 right here, the slope of the tangent line. Of course, right here, we didn't go over those as well. So if I were to graph my corresponding point, it seems like the corresponding point would have the slopes of the tangent line would be 0 at every pi over 2 incidence. And then it would seem to be positive at 0. So it's going to be somewhere at the highest, which is somewhere up here. Let's make it somewhere up here, even though we don't know exactly where. Here, here, and here, and here. And it would seem to be lowest, in other words, the highest negative value at points like, let's make it somewhere down here. Oops, I don't have enough room. Here. Oops, let me make that bigger. Here, here. Excuse me. And here. Okay. So if I were to draw the corresponding function, because it would seem to look something like this, and I'm not the best artist, so let me get it would seem to be something like this, 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 this. And that looks very familiar. In fact, it looks very much like this, which is exactly what this is. And more importantly, it seems like the highest is at 1, and the highest slope is at 1, and the lowest slope is at -1. And this looks very familiar. It looks very much like the cosine function. How can we take a look at this in another way? Well, here's a very informal justification that this derivative of the sine function is the cosine function. So if you remember, let's say we have this unit circle, and we have x being the angle that the line makes with the x-axis, and p being a point with the coordinates of x comma y. And if you remember from pre-calculus, the x value of p is the cosine at the x value, and the point's horizontal coordinate, and the y value is the vertical component, which is sine of x, if you remember from trigonometry. Okay, so let's take a look at the difference quotient, sine of x plus h minus sine of x all over h. Well, here's x. Remember, in x we're going to talk about is in radians. And so x plus h would be just a little higher point right over here. Okay, we're going to call this point Q. Okay, so the height of Q is essentially the sine of x plus h. Okay, all right, so now we have something that looks like this, and we're going to call this point A. Some of you may be asking, what is the significance of the point A? Well, if you take a look at the distance between sine of x, the difference between sine of x plus h and sine of x, that difference is this right here. So this is equal to the length of this segment right here. Okay, so that's important to note. And if we take a look at h, as we can see here, is divided by h, which is the angle of rotation that helps create Q. That can be found from geometry to be the distance, the arc length between Q and P. This angle, central angle, is the same as this arc length measure. So we have a way of expressing this difference quotient as Q of A over arc of QP. All right, but remember, h is supposed to be really, really, really small. So if it's really, really, really small, then really the difference between Q and P can look very much like a straight line. And if the difference between, for very small h, means Q and P is a straight line, then that means that we have some type of right triangle situation going on. If this, for very small h, this will be a straight line, and we have a right triangle between Q, A, and P. And the angle here, which you guys may or may not know a property, but this angle measurement right here is the same as the angle measurement of x plus h. Sorry, I don't know why I can't show this. All right, x plus h. So if I want to find the cosine of x plus h, the cosine of x plus h is literally the adjacent side, which is QA, over the hypotenuse, which of course is our arc QP, but is really a straight line for really small h. So in other words, this right here, this ratio of the green over this line is actually the same thing as cosine of the angle x plus h. So this is an informal way of explaining why the sine of the derivative of the sine function is the cosine function, because for really small h, we have a right triangle here, and the cosine of that right triangle is the cosine of x plus h. All right, so I took a lot of time on that because I just wanted another way to show you. Now let's take a look at cosine function. And as you recall, what we did last time was we looked to see where the cosine function had the highest slope of the tangent line, and it seems to be at this location, which means that if I were to graph the slope of the tangent line, it would be at its highest. Let's say this is the highest point up here, 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 and here, and then it would be 0 at this point. The slope of the tangent line, I mean. So that would mean the slope would be 0 here, slope of the tangent line. And then it would seem to be at its largest negative value right over here. Oops, I'm in the wrong color. This one, this one. This is the highest negative value, which would mean that the slope would be, of the tangent line would be, the lowest it could get would be somewhere, let's say, down here. And so if I were to connect these using my lovely graph, I would get something that looks like this. Oh, I forgot the 0 here. I don't know where. Vice versa, you know what it looks like. Sorry, I can't draw, but y'all know what I'm talking about. And that looks very similar to the sine function as well, as we can see. But this is the derivative of the cosine function, how it would look graphed, and it seems to be very similar to what we just did up here. Just can't draw. Where the height is 1 and the lowest value is -1. Okay? All right, so why is that important? Sorry, I spent a lot of time drawing. Well, that looks very much like the sine function. So, but it's a little bit different because if you recall, the sine function doesn't look exactly like that, because the sine function would be like this. So it seems like this is a transformation of the sine function, and there's several ways you can look at the transformation. I'm going to say it's a shift Either a shift to the left or it's a reflection. And it's going to be easier to consider it a reflection of the sine function so that across the x-axis, which would be negative sine over x. So many ways to look at it, but this is another rationale. So the derivative of a cosine function is the negative sine function. Now let's take a look at another trigonometric function, which is the tangent function. And we're going to use a quotient rule to be able to figure this out. So the tangent of a value x is equal to the sine over cosine of that function. And using the quotient rule, the low d high minus high d low all over low, we get something that looks like this. And as you notice, cosine plus sine squared is 1. So then really the derivative of the tangent function is 1 over cosine squared x function. And to see that graph, you could put that in the graphing calculator. And very quickly, the derivative of the other trig functions, if we convert the other trig functions in terms of sine, cosine, tangent, then we can use the quotient rule or the power rule, however you want to call it, and the chain rule to be able to come up with its corresponding derivative. So these are important to know. I suggest you memorize that so that you'll be at an advantage. Okay, that's it. Talk to you later.